So we'll start. So yesterday what we have done is, so we took a cylindrical pore, something like this, and then the concentration here is CAS. The catalyst is dispersed throughout the pore. Then, so what we have done is, we have derived the concentration profile inside the pore. This is what we have done yesterday. What you do get the equation, the out extreme concentration is CAL. So why do we need to derive concentration profile? Because this concentration profile, this gives clue of the extent of diffusional resistance. Diffusional resistance. Clear. So if the concentration profile is too sharply declining, that means particles are finding resistance to enter inside the pore. Suppose if the concentration profile is, let's say, almost flat, there is no change in the concentration profile, that means particles are freely moving in and out of the pore. So that is what is, let's say, the conclusion. Then what did we get the equation as? Ca divided by Cas is equal to cos h L minus x by cos HML. So remember, here we are deriving the particles are diffusing. Here particles are diffusing in the direction of L. It's clear. Same pore can have another derivation where particles are diffusing in the direction of R. So that is also possible. So here particles are diffusing in the direction of L. So X is diffusing dimension. X is diffusing dimension, whereas R is non-diffusing dimension. So somebody is asking why pores are there. Why pores are there? Because the entire catalyst is a highly porous structure. So that you diffuse the entire, or let's say you disperse the entire catalyst onto the surface. Clear? So this is what we have done. Can you take, let's say, 1 minute time and see what we have done yesterday? So what we have started is a catalytic reactions. We want to know what is the effect of catalyst on the reactor design. Then we understood how many new resistances which are coming into picture because of the catalyst. So how many is, like, you have a gas resistance, you have, let's say, film resistance, and you have, let's say, mass transfer, internal mass transfer resistance, then finally reaction. Within the reaction, then you have three more. One is adsorption, another one is surface reaction, another one is desorption. So these many resistances are coming into picture. Then what this chapter is focusing is only the diffusional resistance. So then how do you, let's say we wrote two questions. How do you know that, let's say, diffusion is governing the rate of reactions? Then what we have written is, so we have written a pore and then we have started, let's say, the concentration of the I think there is, sorry, there is some audio connection back, so I just muted. So somebody is asking what is diffusing dimension. Diffusing dimension is particle is traveling in the direction of, let's say, x. So particles can travel in the direction of r also. No? That derivation is different. So we are doing particles the diffusing direction as, let's say, x. That is what is diffusing dimension by non-diffusing dimension. That is one of the questions. Clear. So with this one, now I got a concentration profile which is, let's say, Ca divided by Cas is equal to cos hm into L minus x by cos hm into L. So what is m? Yesterday what we have written m square as? What we have written m square as? 2k double prime divided by d into r. So this 2k double prime by r, I am combining it, let's say, k triple prime, which is d. So what is basically m is root of k triple prime divided by d. Clear? Now, this is my concentration profile. Now I will draw the concentration profile. Let's find what is the exit concentration, which is Cal by Cas is equal to cos hm into L minus L divided by cos hm into L. So cos h0 divided by cos hm into L. What is cos h0? 1, no. So what is Cal by Cas tells you is 1 by cos hm into L. Now this Cal divided by Cas is a function of m into L. Let's take ml is equal to 0. Then what is your Cal by Cas? What is Cal by Cas? What is cos h0? 1. Suppose ml is equal to, let's say, 0.1. Then what is Cal by Cas? Can somebody calculate what is cos h 0.1 and tell me? Cos h0 is 1 by 0.005. What is 1 by 1.005? 0.99. Suppose ml is equal to, let's say, 10. ml is equal to, let's say, 10. Then what is Cal by Cas? Almost 0. Almost 0. Okay, somebody tries ml equal to, let's say, 1. What is Cal by Cas? Point 648. So now let's go back here and then draw this table. ml is equal to 0. Cal by Cas is 1. ml is equal to 0.1. Same is 0.99. ml is equal to 1. 0.65. ml is equal to 10. 0. So what does this mean is, if I take this 4, something like this, and if I draw the concentration profiles, let's say I'll extend the concentration profiles here. If I try to draw the concentration profile is constant, exactly same. So this is what is Cl, this is what is Cas. So when ml is equal to 0, it is almost constant. Suppose ml is equal to, let's say, 0.1. This is almost, let's say I start with 100 Cas. then this is 100 exactly. This is, let's say, 99. Then this is how the concentration profile. Let's say this is 65 when ml is equal to 1. And then this is almost equal to 0 when ml is, this concentration profile is 0. So basically, what you should note down is the concentration profile. The concentration profile is basically a function of ml, because ml is the one which decides the concentration profiles. No? Understand? So will stop for some time. So just understand what I'm trying to do is, for various ml values, I'm trying to draw the concentration profiles. L is the axial length of the pore. Correct. Ca is concentration on the surface. So what do you say from here is diffusion resistance depends on ml. Depends on ml. The diffusion resistance depends on ml. Right or wrong? Is it right or wrong? Diffusion depends on ml. Right. Clear. Now, this ml is an important factor in diffusion. So this ml is an important factor, which is what we call it as Thiele modulus. What you define Thiele modulus is m into L. What is m into L is K triple prime divided by D into L. This L may not be L. This L can be dP also. Diameter of the particle or diameter, because basically what L stands for is diffusing dimension. Suppose if the particles are diffusing in the direction of X, it becomes L. If the particles are diffusing in the direction of R, it becomes R. Basically what is diffusing dimension. So this Thiele modulus is extremely important. That is what we call it as phi. Then we will define when phi is less than 0.4, we can say that it is, you can neglect the diffusional resistance. That is what we call it as weak pore diffusional resistance. When phi is less than 0.4, you can say that this is weak pore diffusional resistance. That means brackets Y concentration profile is almost constant. Concentration profile is almost constant. When phi is greater than 4, then we can say that the resistance is strong. Why 0.4 is taken? Somebody is asking the question. So why Reynolds number greater than 2100? You are dictating it as, let's say, less than 2100. It is laminar flow. No, why 2100? So these are some experimental values. That means it is lot of experiments are done and decided, let's say, strong for diffusional resistance. So this is what is your first question answer. What did you write the first question? How do you know that, let's say, diffusion resistance is strong or weak? Or let's say, how do you know that diffusion resistance is governing my rate of reaction? So if phi is Thiele modulus is greater than 4, then you can say that diffusion is governing your rate of reaction. Suppose if your diffusion is, let's say, weak pore diffusion, then phi is less than 0.4. Just take a 2 minutes time and read the entire theory again, right from the starting, chapter 5. ML is 5. In the middle is transition region. So what I said at the end is, if the phi is less than 0.4, we can say that diffusional resistance are negligible. That means concentration profile is constant throughout the pore. If phi is greater than 4, it is strong pore diffusion ratio. So we'll go to next board. So what does, let's say, phi less than 0.4, how does this look like is, the pore is something like this. The concentration of SC, let's assume that 100, then it is almost 100 throughout the pore. 100, 99, 99, something like this. If phi is greater than 4, then what happens is the concentration profile 100 here, maybe 99, 95, let's say 90, 80, 70 and 60, maybe something like this. So basically it is almost constant here. The concentration profile is constant. The concentration profile is dropping. This is what is difference. Clear? Now, suppose, let's assume that, suppose if phi is greater than 4, if phi is greater than 4, then my rate of reaction RA is equal to K into CA. Which concentration should you substitute in CA? What is the concentration available for the reaction? Is it 100 or let's say average of these values? So what to substitute? What to substitute in place of CA? Which value do you substitute? Should you substitute 100 or let's say average of all the concentration inside the pore? So ideally what we substitute is, because the catalyst, where is the catalyst? Catalyst is sitting here, no. The catalyst is seeing this concentration. So we have to substitute average of concentration inside the pore. If it lies in between 0.4 and 4, then it is transition. Clear? So what I can measure is, this is what is gas phase concentration, no? So this is what is gas phase concentration. What we can measure is only the gas. Suppose if I put, let's say, concentration measuring device into the reactor, and if I see the concentration, do you get the concentration of the gas? Clear? You get the concentration of gas only, no? Now, the measurement of concentration inside pore is not possible. Because pores are, they are not like, let's say, some of the big volume pores where you can put probe inside the catalyst. So catalyst itself is, let's say, small particles, and inside the small particles there are pores are there. So you cannot measure the concentration of the particles inside the pore. Clear? So you cannot measure the concentration inside the pore. Measurement of concentration inside the pore is basically not possible. Clear? Then what do you do? How do you design the reactor? So for design, if you are in a strong pore region, how do you design a reactor? Now the question is, how do you design the reactor? Because if I substitute 100 in place of Ca, I'm doing wrong for the reactor design, because my actual rate of reaction available is concentration which is inside the pore, but actually I'm putting the gas phase concentration, which is wrong. So if you are in weak pore diffusion region, then it doesn't matter, because gas phase concentration and concentration inside the pores is exactly same. Clear? So if you are in weak pore diffusion region, diffusion resistance are, let's say, negligible, then it doesn't matter whether I put 100 or let's say inside the pore, because what is the concentration inside the pore is also 100 only. But if you are in strong pore diffusion region, imagine that the concentration inside the pore is less than 100, because it is continuously dropping. Clear? Now what do you do now? How do you solve this problem? Because I can't, suppose imagine a packed bed reactor which is in the plant. If you put a probe inside the plant, does it detect the gas phase concentration, or can you put a probe inside the catalyst pores, which is extremely impossible, because these dimensions are in nanometer in nature. So chromatography, all these techniques are to measure the concentration. I am saying, how do you measure the concentration inside the pore? You cannot put chromatography, all these probes inside the pore, no. Not possible. Then how do you design the reactor? So imagine a scenario, your catalyst is under strong port diffusion region. So I have to design a reactor. Then which concentration should I use? I have to ideally use the concentration which is inside the pore, but I can't measure it. Then what do you do? Then that is where the concept of, let's say, effectiveness factor comes into picture. We will define the concept which is effectiveness factor. So how do you define effectiveness factor? Let's say E, what it says is rate of reaction with diffusion, rate of reaction with diffusion divided by rate of reaction without diffusion. Clear, rate of reaction with diffusion. I don't know, it is going into mute unknowingly in between. So rate of reaction with diffusion divided by rate of reaction without diffusion is what we define it as, let's say, effectiveness factor. So rate of reaction with diffusion, I'll write it as, let's say, K double prime Ca. Rate of reaction without diffusion is, suppose if you assume that, let's say, there is no diffusion, then what is K double prime by Cas, which is what is K double prime Ca by K double prime Cas. Now, if you imagine a pore, take a pore and imagine that, let's say, the concentration here. So the concentration inside the pore, where is no, so the effectiveness factor here is different, here is different, here is different, here is different, something like this. So what is my average effectiveness factor is nothing but integration of effectiveness factor from 0 to L E into dx into what is average is 1 by L. No, this is sum, integration is sum. So this is how you should calculate the what is my average effectiveness factor. So right up to this point, so we'll go to next board. Now, since let's say CRE coming almost end, maybe 4 or 5 lectures are there. So I would recommend you to read the entire CRE again. And if you have any doubts, clear in the classes itself, because it is almost the month of September. So you are almost on the verge of, let's say, the gate preparation. So I would request you to, let's say, daily spend 4 to 5 hours, complete the each classes. This year is very good advantage for you because most of the people might not be, let's say, or let's say, like it is situation is not good, no. So somebody who is actually preparing well will take the advantage of this one. Suppose if there is no diffusion, then the concentration inside the pore will be, let's assume that there is no concept of diffusion, then inside the pore the concentration will be Cas only, no. So how do you calculate average is, let's say, what is E average is equal to 1 by L into 0 to L Ca by CAS into dx. What is CA by CAS? We have written now. What is CA by CAS is cos HM into L minus x by cos HM into L into dx. What is integration? Cos hx integration is, what is cos hx? Minus 1 by ml into sin h m into L minus x by cos h m into L with the limits of 0 to infinity. So what is sin h0? 0 to not infinity, 0 to L, no? L. What is sin h0 is 0. If you put this one, you will get tan hml by, let's say, ml, which is called as tan h phi divided by phi. So what is my average effectiveness factor is tan h phi by phi. Is everybody got it till now? Clear? Now, suppose when phi is, let's say, less than 0.4. So, can somebody calculate, say, what is tan h of, let's say, 0.4 value? What is tan h 0.4? It is almost equal to 0.4. You will get 0.38, which is almost equal to 0.4. So when phi is less than 0.4, what happens here is tan hx, tan h phi by phi. This tan h phi is almost equal to phi, which is actually 1. Now you don't need this value also, but when phi is less than 0.4, what is E? What is E is CA by CAS, no? When phi is less than 0.4, your CA is almost equal to CAS, no? Because your concentration profile inside the pore is equal to CAS. So correct or not? Suppose if phi is greater than 4, phi is greater than 4. Can somebody calculate, let's say, tan h 10 or tan h 5, something like that? You will get almost equal to 1. So that means when phi is greater than 4, your tan h phi is almost equal to 1. So that means what is your epsilon is almost 1 by 5. So your epsilon is 1 by 5. Clear? So if phi is greater than 4, your effectiveness factor is inverse of delay modulus. I think this is almost repeated, I don't know how many times. Every alternate years, or let's say 4 or 5 times given for 1 mark question. When you are in strong pore diffusion region, the effectiveness factor is reciprocal of delay modulus. So everybody is with me till now? Any doubts? Strong pore diffusion is when the concentration profile is dropping. At strong pore diffusion resistance. If you want, if you are confused, then write like this. It is strong pore diffusion resistance. Resistance is strong. Strong pore diffusion So just spend some time. I am giving breaks in between because we will connect the theory slowly. Is everybody clear till now? Concentration will never increase, Baba. Concentration will decrease because particles are reacting. No. Now I'll go to how do you use this formula? Let's say effectiveness factor 1 by 5. Let's imagine that your phi is equal to 5. So if phi is equal to 5, does it come under, let's say, that does the diffusional effects are negligible or let's say not negligible? Can you neglect the concept of diffusion when phi is equal to 5 or you can't neglect? You cannot. So you cannot neglect the diffusion. So basically it is some people will misunderstood as strong pore diffusion means diffusion is strong. It is not diffusion strong, it is resistance strong. In the gate question also sometimes he will give you a strong pore diffusion. Don't get confused with diffusion is strong. It is pore diffusion is resistance is strong. That means particles are finding it difficult. So suppose then what do we do is my rate of reaction, how do I write is I'll multiply K and then concentration which is Ca. What is this Ca? Concentration Ca. Ideally we have to put inside the pores. Concentration inside the pores. Since we can't measure, what I will write it as concentration of the gas multiplied by, how do you do? So what is your effectiveness factor? Rate with diffusion by rate without diffusion. No. So effectiveness factor multiplied by, let's say, rate without diffusion. So what is your effectiveness factor? 1 by 5. So I will take my concentration of the gas into 1 by 5. So you are taking, let's say, if my concentration of the pore is something like this. Suppose if Ca gas is 10, then this is how my concentration is dropping. So ideally, let's say this is 9, this is 8, this may be 7, this may be 6. I have to substitute the average. Since I can't measure the average, what I am doing is I am multiplying 10 with the 1 by 5. So this 1 by 5 will take care of the decrease in the concentration. So how do I calculate rate with diffusion is K into K double prime into CAS into your effectiveness factor. This is how you account for the rate of reactions. This is the one that you should use for the reactor design. For reactor design, you should use this one. By default, the concentration given is concentration of the gas. But you have to go inside the subject. Concentration inside the pores are different from concentration of the gas because the pores are offering resistance. So the concentration is dropping. I have to substitute the concentration inside the pores, which I cannot measure. So what I am taking is, I am taking the concentration of the gas, then I am doing a correction using effectiveness factor. Spend some time, slowly understand into your brain. If it is in between 0.4 and 4, then we have, let's say, another rules. These are not required now. Yes, geometry of the pore, yes, it depends, no, because geometry of the pore is a function of your Thiele modulus, no. Suppose if I have a pore which is long, then your Thiele modulus is high, then you have a diffusional resistance. So I'm doing it for a single pore, no, doesn't matter, all the pores will be same, no. Yes, strong pore diffusion resistance, strong pore diffusion are same. Sometimes resistance word may not be used in the word. So finally, what did I ask in this? What is the second question that I wrote in the starting? So I wrote two questions. One thing is, how do you know that, let's say, diffusion is governing the rate of reaction? Second question, what did I write is, how to design a reactor? So that is what I am saying now. How to design the reactor. How to design the reactor is, suppose if it is CSTR, now volume of the reactor will not come into picture. You will have a weight of the catalyst coming into picture. So if it is CSTR, W by FA naught is equal to XA by minus RA into effectiveness factor. Let's say if I am writing minus RA as, let's say, first order reaction, then what is K into Ca? What is the Ca? Do you write gas phase concentration, or the Ca is concentration of gas? If it is weak pore diffusion, then effectiveness factor will be 1. Then it doesn't matter because concentration of the gas, concentration of the pore will be exactly same. So how do you design a PFR is W by FA naught is equal to integral 0 to XA dXA by minus RA into effectiveness factor. This is my second design of the reactor. Now weight of the catalyst is coming into picture. Volume doesn't matter. Suppose if I have a bigger reactor, maybe 1 kg of catalyst, because reaction is happening only on the catalyst, no. Volume change factors will come in terms of concentration, no. What is concentration? If it is let's say Ca equal to Ca naught into 1 minus Xa by 1 plus Ca Xa, no. If it is liquid phase, no change. W stands for weight of catalyst. Kgs are depends upon the rate equation. What is effectiveness factor is 1 by 5 m. What is effectiveness factor is 1 by 5. Are you clear till now? So this is, let's say, completion of, let's say, the theory. So I will give, let's say, 4 or 5 minutes time. Now read the entire theory from starting to end and get an idea. What is a catalyst? We have defined what is the role of catalyst. How does catalyst looks like? How does molecules enter inside the pores? What are the resistances coming into picture? Then what is diffusion? So we have done something like a story kind of thing. Hey. So are you clear? Yes, yes. 5 greater than 4, it is 1 by 5. So I'm giving, let's say, I'm giving 4 or 5 minutes time. So I will be on mute. Just understand the theory right from the starting. diffusion followed by reaction is a series. No, first, see, imagine it will not occur simultaneously. It has 3 gates in series. First molecules has to cross gas, then molecules has to cross diffusion, then they have to cross reaction, then they have to start reaction. These are in series. Somebody is asking for strong diffusion, CAS, CA are same. It is not. Strong diffusion means strong diffusion region. So CAS will be dropping. So I drawn the profiles now. Strong pore diffusion resistance and strong pore diffusion are same, because see, they actually implies opposite, but that resistance word is generally missed in the conversation. Strong pore diffusion resistance. So forget about strong pore diffusion. Now onwards, write strong pore diffusion resistance only. Now, once you are done, let's say, does everybody has studied up to till now? The entire thing? Everybody understood till now, whatever we have studied? No confusions, no doubts, nothing. Now, this is what is, let's say, this thing. Now, in the lab scale, in the labs, or let's say, experimentally, how to find, let's say, whether it is strong pore diffusion resistance or let's say weak pore diffusion resistance. One is calculate phi. Calculate phi. So what is phi formula? Root of k triple prime divided by d into dp r l. It can be anything. Basically diffusing dimension. Somebody will confuse it. Let's say I have r inside this k, so r should go here. That is not r actually. That is basically diffusing dimension or non-diffusing dimension. That is how you should write that one. Clear? Now, let's say sometimes what happens is I don't have, let's say, right D values, I don't have right K values. Then what happens is generally we need to depend upon the experiments. We need to depend upon the experiment. So what I will do is, let's say I'm doing a reaction with N2 plus 3H2 gives, let's say, 2NH3 reaction. Then what I will do? So I will take N2 plus 3H2 mixture. Then I'll pass it to a small reactor where I load, let's say, 5 to 10 grams of catalyst, 5 to 10 grams of catalyst. Then I'll see, let's say, products are forming. Then I'll analyze in the GC, gas chromatography. I'll see how the rate of reaction is there. Suppose after doing experiments, from experiment, my rate of reaction which I found experimentally is, let's say, 10. What does this mean is, this rate of whatever you observed from the experiments, this is what is your rate of, let's say, overall. Whatever you found, this rate of overall, rate of experiments, or this is nothing but a rate of overall. So this rate of overall may be, so this may be rate of gas film, may be rate of diffusion, may be rate of reaction, because these three are occurring in series. No, rate of gas film, rate of diffusion, rate of reaction are occurring in series. Whichever the slowest step, or let's say whichever the slowest of all, will govern the rate of overall reaction. Clear? Is it clear till now? Is it clear till now? So whatever the experiments that I observed, rate from the experiment is 10. This 10 could be rate of gas film, 10 could be rate of diffusion, 10 could be rate of reaction. We don't know which one it is. Now, next question is how to know, let's say, which one is, or let's say, which is controlling the, what is SPDR abbreviation? Strong core diffusion resistance. Now somebody is asking that. How to know which is controlling the overall rate? Now, how do you do this is, so how many rates you have? Rate of gas film, rate of diffusion, rate of reaction, my overall rate. So one of this is controlling the, one of this is controlling my rate of reaction. So what do I do is, so this rate of gas film, slowest of this rate of gas film is a function of stirring speed, or let's say, if I am doing, let's say, liquid phase, or let's say if I am doing experiment in a gas, let's say CSTR, that stirring speed will define how much is the film thickness, then which defines the rate of gas film. This rate of gas film is stirring speed. So what is rate of diffusion? This is depends upon the function of phi, which is Thiele modulus, which is nothing but function of m into dp. Basically, it is a function of dp. So what we can write here is, I will change the stirring speed, I will change the stirring speed. If you change the stirring speed, then what happens to your gas film? Then what happens is your gas film rate of gas film changes. Is it changes or not? If I change the stirring speed, then my rate of gas film changes. Suppose if rate overall changes, then what does this mean? Suppose if my rate overall changes, then what does this mean? If rate overall changes, then this means that my rate overall is a function of basically gas film. That means gas film is controlling. So this is indirect way of finding. So basically this is how you mentally. So experimentally I have done experiment at a steering speed of 100 rpm. If my 100 rpm, I have some rate. I have 200 rpm. If my rate is same, then what happens is I'm changing the film rate, but my overall rate is not changing. That means my overall rate is not linked to film. Overall rate is linked to somebody else. So basically what I do is I'll change the steering speed, then rate of gas film changes. If the rate of gas film changes, then if the rate overall changes, that means there is a link between these two. Have you understood? So if there is a link between this, so that means your overall rate is governed by gas film. Just understand. Just spend some time. I will explain one more time. Even if you take PFR also, how do you change steering speed? You increase the gas velocity, you decrease the gas velocity. If you increase the gas velocity, then the film thickness decreases. If you decrease the gas velocity, then film thickness will be more. So this is how. So basically, if RPM changes, then if my rate of experiment changes, then film is controlling. So I'll repeat again, last part. See, my rate of overall either depends upon gas film, diffusion or reaction. This is what you observe experimentally, So what I do is, intentionally I'll change the film resistance. Intentionally I'll change the stirring speed, which affects my rate of gas film. Suppose if this is affecting my overall rate, then that means rate of overall is linked to gas film. I'll change my diameter. If that diameter changes diffusion rate, if that is changing my overall rate, then that is my overall rate is a function of diffusion. Then reaction. If these two are not controlling, then reaction is controlling, no? Something like this. So if dia of particle, generally we refer to not pore diameter, particle diameter, because if particle diameter is big, pore diameter is big, all are proportional. If dia of particle changes, if my rate that you are observing experiments is changes, then diffusion is controlling. So this is how. RPM change for steering speed, no? RPM of the motor. Film and external mass transfer are same. This I have already repeated many times. When I am defining the class initially itself, film stands for external mass transfer. Diffusion stands for internal mass transfer. So if you are done here, then we will solve one problem. Just spend some time, understand this one. So I will write one problem. Just understand the concepts again. Write this problem. Diffusion means both. All diffusion, particle diffusion and atom diffusion, all. So write this problem. Following isothermal kinetic data, is obtained is obtained in a basket type of mixed flow reactor for a porous catalyst. Determine the role of pore diffusion and external mass transfer processes. So 4 columns, these are given. So the question is, following isothermal kinetic data are obtained in a basket type of mixed flow reactor for a porous catalyst. Determine the role of pore diffusion and external mass transfer processes. This is the data which is given. Determine the role of pore diffusion and external mass transfer. Basically, which one is controlling? Third column is spinning rate of the basket. Here you have done 3 experiments. What is the answer? Pore diffusion is controlling or mass transfer is controlling? Somebody is saying pore diffusion is controlling, somebody is saying film resistance is controlling. Let's take first two data points. Let's take these two data points. You are changing the diameter, you are changing the steering speed, your rate is changing. Can you make any conclusion here? Does my rate is changing because of pellet diameter or spinning rate? You will like from this one, no conclusions. Because my rate can change because of pellet diameter or rate can change because of steering speed. Clear, no? Now let's take these 2 points. From these two, what you can conclude? My diameter is same, but I am changing my steering speed, but my rate is not changing. So my rate overall is not a function of RPM. So what does that mean is mass transfer does not control the rate of reaction. Mass transfer does not control the rate of reaction. Then what I do is I will take 1 and 3, like these two experiments. Suppose if you take these two experiments, then what is change? If you see first and third experiments, I am changing diameter, my steering speed is same, but my rate is changing. Clear? So basically my rate overall, what you can say is a function of diameter. That means diffusion is controlling. Diffusion is controlling. So mass transfer is not controlling because if I change the steering speed, I don't observe any, let's say, change in the rate of reaction. So diffusion is controlling. Suppose if diameter increases, what happens to your rate? Does rate decreases or increases? Decreases. So because if my diameter of particle increases, what happens to your Thiele modulus? Thiele modulus increases. If Thiele modulus increases, then what happens is concentration drops more or not? Drops more, which is my rate overall decreases. Or else your rate overall is a function of K into Ca power n into effectiveness factor, which is a Thiele modulus. What is Thiele modulus? K into Ca power n, 1 into m into dp. See, for a first order reaction, basically my rate is inversely proportional to diameter. That is why in the previous case, if you see diameter increases by 2 times, my rate decreases. So all these stories are under strong pore diffusion resistance region. If you are under weak pore diffusion region, then your story changes. So if I have a catalyst which is under weak pore diffusion region, that means Thiele modulus is 0.1. Suppose if I am increasing the diameter, you are moving from weak pore diffusion to strong pore diffusion. Suppose if I have ammonia catalyst, when I make small pellets of let's say 1 mm dia, my Thiele modulus turns out to be 0.1. Suppose this low particle diameters, or let's say when you have a particle diameter low, then what is the advantage? When the particle dia is low, suppose my particle dia is low, then what is positive point is phi is less. What is negative point is pressure drop is more, delta P is more. Because if I load small powder type of catalyst in the reactor, then what happens? You have more pressure drop, no? Suppose if my dP is high, then what happens? What is negative point is your phi is high. What is positive point is my delta P is less. So you have to balance between the delta P and let's say Thiele modulus. So suppose for an ammonia reaction, which is a weak pore diffusion, doesn't mean that always ammonia reaction will be under weak pore. A same catalyst can go from weak pore to strong pore if you change the diameter of the particles. If you make bigger particles, it will go to weak pore, strong pore diffusion. If you make smaller particles, it will go to weak pore diffusion region. Yes, in the question he has mentioned diameter means the diffusion is occurring in the along the direction of D. That is what, whatever the dimension given in the question is what you need to understand as the diffusion dimension. So we will stop the class here. It is almost 7:58. So if you have any questions, big particles, small pores are not particles possible. No, big particles, small pore. If the particle is big, then pore is also big. No. So we'll doubt the second and third column. I think we have explained. Can you repeat the last point about bigger particles? So if you have, let's say, bigger particles, then my Thiele modulus is more, which is a negative point, but I have a low pressure drop. The concentration we are trying to is concentration drop after diffusion or the concentration that we are writing is the concentration of the gas. Ideally, I have to write the concentration inside the pore, which I can't measure. That is why I am multiplying with the concentration with the effectiveness factor. So it is not, what is phi is root of k triple prime divided by d. What is d is diffusion. But that root of t k triple prime is nothing but 2k by r. What r is not the diameter. R is the non-diffusing dimension. From the first dp1 third dp2 pellet size, there is also no conclusion because the rate is, there is a conclusion no, from 1 and 3. 1 and 3 will not get any, 1 and 2 will not get any conclusion. That is what I explained again. 1 and 2 you will not get any conclusion because I am changing diameter, I am changing steering speed, you don't know which one is changing. Clear? Another doubt. If the diameter is increasing, we are moving, if the diameter increases, we are moving from weak pore to strong pore, no? What is diameter? Thiele modulus m into dp, no? Then you are moving, increasing direction of Thiele modulus, no? So here one more important point is, what is R stands for radius, non-diffusing dimension. Suppose m into, maybe I'll take another board. So what is m into dp? So what is m? Root of k triple prime by d. What is k triple prime? 2k double prime divided by not r now, because since I use the diameter here, this will not be r. This will be what is non-diffusing dimension. Maybe L, maybe something else. So this is a constant. That is why we have sent inside the k. That is why I have written it as a simple constant. That you should not worry about. So what is another doubt is, what is R I have explained. So I'm explaining something in between. So I think here, if you see, interestingly, leaving concentration of reactant is given. Why leaving concentration he has mentioned? Because it is a CSTR. The concentration available for the reaction is the leaving concentration. So another doubt is, strong pore diffusion resistance are on diameter because you are taking the diffusion in the direction of D. If your direction, so don't get confused with the DPRL. Whatever given in the gate question is the dimension where the particles are moving. The non-diffusing dimension you should not worry about. Don't hung up on, let's say, that R which is inside the root. That R can be L, that R can be something, but that is a constant. That is why I have sent inside the K. I have simply written as K triple prime divided by D. So I think we are not getting any doubts more. So I'm closing the session here.